right, so thus far in our journey into mass spectrometry, we have mostly focused on determining the molecular mass of a compound that's produced in the spectra. And doing that, we've identified the molecular ion peak and then kind of looked at some other clues that the N+1 and N+2 isotope peak can give us about the structure. Now, other fragment peaks and their relative intensities can give us important information about a molecule's structure as well. We mentioned this in the first couple screencasts, but I just want to remind you, fragmentation pathways are the chemical processes that are responsible for producing fragment ions. Okay, now a few things here. These are going to depend on the structure of the molecule and the functional group. So we are going to look at things based on some structural issues here throughout this screencast, as well as some functional groups. Okay. So let's first start by discussing alkanes, which don't have any functional groups. And then we are going to look at the fragmentation patterns of alkenes and aromatic compounds. Those CC double bonds and how they may lead to some fragmentation pathways. Then we're going to talk about alkyl halides, amines, ethers, and alcohols, which all have functional groups that are singly bonded to a heteroatom. And then we're going to cover things in the carbonyl family like ketones, aldehydes, and carboxylic acids. So without further ado, let's continue on into alkanes. Now, alkanes don't have a functional group. This is the mass spectrum of hexane, which was previously discussed in one of our screencasts. And this is where we first really started talking about fragmentation pathways. We know from this, right, that we have our molecular ion peak here. It appears at 86, which corresponds to the molecular weight of hexane. Now, we also know that that fragment right there is produced by the loss of an electron from any one of hexane's sigma bonds, okay? And so the molecular ion that produces this, because we don't exactly know which bond it comes from, is just represented by placing square brackets around the parent molecule along with the dot and the positive charge to indicate that radical cation. Now, if we look at this, we've got several key fragment peaks that can also be identified at an M to Z of 71, 57, 43, 29, and 15. And these are going to correspond to the breaking of various carbon-carbon bonds in hexane, which we walked through. We can see here, for example, right, the base peak at 57, which is showing here, corresponds to the breaking of this C2 and C3 bond, and it produces the butyl cation and then the ethyl radical. Now, the mass to charge peak at 15 corresponds to the breaking here, where you get a methyl cation and then a pentyl radical. Because the peak at that mass to charge of 57 is a lot more intense than the one at 15, we know that fragmentation pathway that's here is more likely than the fragmentation pathway here. So again, I just want to recap. In the previous slide, 57 had more intensity than 15. That leads us to believe that this happens with more molecules than this does. Okay? So why is this? Well, in general, what we can say is that a fragmentation pathway becomes more likely as the stability of the fragment ion that produced fragment ion produced by that pathway increases. Okay, so let's notice a few things here. I want you to notice that, because maybe the burning question you heard is why. I want you to notice here that this cation is a primary carbocation, right? Which is much less stable. Wait, I think I've gotten it backwards. Hold on just a second. I didn't write it at the right place. Sorry, this is a methyl cation. And this is a primary cation. Sorry, I thought I wrote it too low. So we've got a primary cation here, and that's a methyl cation there. And the methyl cation is much less stable than the primary cation. And so because this is much less stable, this is a lot less likely to happen. Because the primary is more stable than the methyl, this fragmentation pattern is more likely to happen, which is why we tend to get that increased abundance at that mass to charge of 57. Now, let's look at some other molecules with fragmentation patterns where stability also guides their fragmentation patterns. Let's look at 2-methylpentane. So we have 2-methylpentane here. It's got the same number of carbons and hydrogens, so its molecular ion peak here is at 86. And I want you to notice a few things. Notice the base peak here is at 43 instead of 57 where hexane is, okay? So the fragmentation that accounts for that base peak at 43 is shown here. So we have this fragmentation pattern. Now this pathway is favored because it produces a secondary cation, right? So that's a secondary cation, where another fragmentation pathway, say if you had a fragmentation pathway right here, that would produce a primary carbocation, which is a lot less stable. And that, where the green is, that would give you 57. So stability can help us with these particular carbocation stability can help us predict which fragments are going to be larger. Now, when you have increasing branching, what we find is that fragmentation is going to give rise to relatively highly stable fragment ions, because with more branching, you get more secondary, tertiary, and so on. So let's look at 2,2-dimethylbutane. Notice here, right, if we go back and we compare this to hexane, I want you to look at the size of the molecular ion peak there. Notice that it almost disappears. It's much smaller than hexane. What this indicates is that fragmentation is much more likely for a molecular ion of 2,2-dimethylbutane, because what we see is with additional branching, those fragment ions that are more stable can be produced. So this has more branching, so the fragments that are produced are more stable, so the molecule is more likely to fragment as it goes through the instrument. So we can make kind of this summary between the last three mass spectra that we looked at, that if a fragment ion is sufficiently stable, then the molecular ion peak can essentially disappear from the compound spectra. Okay. Now, you are going to notice in your packet that you are going to have some compounds where their molecular ion peak has completely disappeared. One of the ways for this to kind of be a hint is that to look at the x-axis, and if there's kind of an extension, a long extended x-axis here, then there's probably a molecular ion peak in there somewhere. And I try to point those out to you, and you'll notice those in your packets. Okay, so we've talked about alkanes. Let's talk about what happens when you have a double bond. First off, now we have pi electrons, right? So with alkanes, we just had sigma electrons, sigma bonds, but now we've got some pi bonds. So that means we've got pi electrons. Now, these pi bonds have a relatively high energy compared to the sigma bonds. So it's usually one of these that are ejected in the ionization process to produce a molecular ion shown here. It doesn't affect the molecular weight. So notice for hexene, the molecular ion peak is 84. But that's generally what's happening there is when you have a double bond or a triple bond, we've got those pi electrons. Those tend to be the electrons that are ejected first. Now, because of this kind of relatively well-defined nature of the alkene's molecular ion, fragmentation pathways for alkenes tend to be really clear-cut. So when we look at this, here is our alkene. So we've lost an electron. Here's that in mass to charge ratio at 84. What you're going to see here is that an ethyl radical is expelled. So we have an ethyl radical here that's expelled, and we end up with a butenyl cation. Now, right, when we look at this, what we can say just generally is an alkene's molecular ion tends to expel an alkyl radical from an allylic carbon, right, which produces an allylic cation, right, in the form of a carbon with a double bond to a carbon next to a carbon with a positive charge. And so you can see that right here. Okay, there's a carbon, double bonded carbon next to a carbon with a positive charge. This happens because there's resonance, right? And we know that resonance stabilizes things. So when we look at this fragmentation pattern, right, we can see that this is resonance stabilized, and so we end up with a fairly large mass to charge ratio at 55. And if you go back and you look, we can see that that's our base peak. That's going to be our largest peak. And the reason for that is because of resonance. Now, let's talk about benzyl cations just for a hot minute. We have some similar fragmentation patterns that are observed with our benzyl cations for these aromatic compounds. What we're going to find is that aromatic compounds are fairly stable, so they tend to be really nicely stabilized. So what you're going to tend to lose, just honestly, is you're going to lose these guys first, right? So what we can say then, if we want to put words to that, is the molecular ion alkyl benzene tends to expel an alkyl radical from a benzylic carbon, and that produces a benzylic cation. Okay, so the molecular ion peak is here at 134. Notice, right, that if you take 134 and you subtract 91, let me pull out my trusty calculator. That gives you 43. So that's the difference from here to here, right? So that's a mass loss of 43 there. And so when we look at that, what we're seeing there is this propyl radical. And so we're saying, hey, look, that's probably the difference between there and there. So if you take right, if you take these 3 carbons, that's 12. So 12 times 3 plus 7, that gets you close to 43. And so that's what we're seeing there. And so this will tell it much more eloquently than I was trying to on the previous side. When you look at that loss of a propyl, right? So the spectra said, hey, look, we're probably losing a propyl. And so the question, of course, is why? Why are you tending to lose a propyl? Why is this more stabilized? Well, we have resonance. So we lose this group, right? And this is our propyl radical, so it's gone because it's not charged. We can't detect that. So what we see here, though, is because there's a positive charge here, we end up with resonance stabilization. And so with this resonance stabilization, you end up with a benzyl cation. Now, a wickedy wild thing that happens, which is super interesting, is that in the gas phase, this benzyl cation is believed to rearrange to a tropylium ion, which is shown here, which is an aromatic 7-membered ring, which is pretty interesting in and of itself. But the resonance is why we get that large peak there at 91. Well, let's look at some other heteroatoms. So let's look at alkyl halides, amines, ethers, and alcohols. So many functional groups contain heteroatoms, right, which really affect these fragmentation pathways. One of the most important features of heteroatoms is they have non-bonding lone pair of electrons. So if we think about it, right, any sort of halogen, which I'm going to represent with an X, that's a chlorine, fluorine, bromine, or iodine, has a bunch of non-bonding electrons. Amines, unless it's a quaternary amine, generally you're going to have a lone pair of electrons. Ethers, right, we've got that oxygen with 2 lone pairs of electrons. Same kind of deal with alcohols there, right? We've got 2 lone pairs of electrons. These tend to be the least tightly bound electrons in the molecule. They're non-bonding electrons, so they're not going to be tightly bound. And so what we find then is that in the ionization of a molecule containing a heteroatom, lone pair electrons are generally the most likely electron lost to produce the molecular ion. So as before in alkanes, where we were losing an electron in the sigma bonds, or in double and triple bonds where we lose an electron from the pi bonds, well, now when you get heteroatoms, we tend to lose electrons there. And so what does it look like for us? Well, if we look at alkyl chlorides, right, the loss of a non-bonding electron from the chlorine shows here, right? And it produces a molecular ion with a mass to charge ratio of 106. So again, we're not changing the mass here, but now this chlorine is carrying a positive charge. And so what happens is you end up with heterolysis, and that this bond here breaks, okay? and that produces an alkyl cation here with a mass to charge of 71. Now, because that fragmentation takes place pretty readily, and so that you don't get a molecular ion peak there. So that's one of the ways that you would not get a molecular ion peak. Let's look at another common fragmentation pattern, which is alpha cleavage. Now, alpha cleavage is just the elimination of an alkyl group from the carbon atom bonded to the heteroatom. Let's pretend like I spelled heteroatom really well there and clearly, right? Bonded to the heteroatom. So we're losing an alkyl group. This is an example of alpha cleavage where we're going to lose this methyl, okay? Now, the methyl that we lose is the one bonded to the carbon next to the heteroatom. So notice if we lost the CH3 over here, that would not be alpha cleavage, right? We have to lose, right, this, or there, anywhere those three lines are, for that to be considered alpha cleavage, okay? Now, when this occurs, and there happen to be two alpha cleavage pathways for this particular molecule, right? Because there's symmetry here, those are the same groups. So when we look at this, these two account for the peaks that you can see on the previous spectra at a mass to charge ratio of 99 and a mass to charge ratio of 71. Notice here in the resonance structures for each fragment ion, all the non-hydrogen atoms have an octet, and that's really what's going to provide the driving force for this process, right? Is that we're getting octets here. The two fragmentation pathways that we saw, which was heterolysis on the previous page and alpha cleavage, are characteristic of other compound classes that contain functional groups with heteroatoms, like the amines, ethers, and alcohols. Now, depending on the identity of those functional groups, as well as the specific structure of the compound, one of these fragmentation pathways can be highly favored over another. And so while we can make some large generalizations, sometimes it does come down to the molecule itself. Now, alpha cleavage is very common for amines. So when we look at this, what you can see here, right, is there's your heteroatom, there's the carbon attached to the heteroatom, and this is considered the alpha cleavage there. That CH3 group is eliminated. This forms an iminium ion. That iminium ion has a carbon-nitrogen double bond here, and that's very, very stable. So you get this peak at 86. It's our base peak there. Our molecular ion peak is here at 101. We also see alpha cleavage in ethers, as well as alcohols. It's typically not as prominent as is in amines or your halogens. If you look at the mass spectrometry of diisopropyl ether, which you can see here, fragmentation via alpha cleavage does give rise to the peak right here at 87, but it's significantly smaller than this base peak at 45. Likewise, if we're to look at 1-pentanol, okay, we notice alpha cleavage gives rise to a relatively small peak here at 31. And it turns out that mass peak there at 31 is a signature of primary alcohols as well. The reason is, when we look at this, alcohol 16, so this guy has a molecular weight of 17. This is 14. If you're cleaving here, right, that's alpha cleavage, then 14 plus 17 gives you 31. That's why that's a signature of primary alcohols. Now, there are other cleavage pathways that are really prevalent in alcohols. One is the loss of a hydrogen atom, which gives rise to a MH peak that is 1 atomic mass unit lighter than the molecular ion peak. And so if we look at that, that's shown, well, it's shown there, right, where we're losing that hydrogen atom. The other one we'll see is the loss of a water molecule, and that is shown here in number 2, and it gives rise to a peak that's 18 atomic mass units lighter than the molecular ion peak, right? So that's where we see that. It's 18 units lighter. Now, that cleavage is a lot less straightforward. It is going to involve the simultaneous cleavage of the carbon OH and then this carbon hydrogen bond. So this OH group here and this hydrogen bond here, let's see if I can highlight those for you. The OH group here and the hydrogen bond here are what go to form that water. And again, that water has a molecular weight there of 18, and so that's why we see a peak that is 18 less than your molecular ion peak. Now, carbonyl containing groups, so similar to other functional groups that we've covered, are things like ketones and aldehydes and carboxylic acids. These also have an oxygen atom that have a lone pair of electrons. Now, as a result, these compounds tend to undergo ionization and fragmentation processes that are similar to those alkyl halides we just looked at in amines and ethers. Specifically, the molecular ion of carbonyl containing compound is typically produced by loss of a lone pair of electrons from the carbonyl oxygen. So what we see here, right, is the loss of that lone pair of electrons, loss of one lone pair electron from, right, the oxygen. So when it ionizes, we're going to lose an electron from that oxygen. Now, when that occurs, alpha cleavage is really common, resulting in a psyllium ion, which is represented here with this carbon-oxygen bond. Okay, so it's a really common fragmentation pathway. Now, that subsequent alpha cleavage can expel a butyl radical from the carbonyl compound, and that produces that really relatively stable psyllium ion, and that's what gives rise to this base peak here at 43. And then notice also here at 85, that's where that methyl radical produces the ion corresponding to the mass to charge ratio there. So we get those two fragmentation peaks from some pretty specific cleavages. Now, one of the most well-known and well-named fragmentation pathways, and remember, I've taken a whole class on mass spectrometry that spent a lot of time on different fragmentation pathways for different molecules. So we're just really dipping our toe in the ocean of fragmentation pathways. But this is a named rearrangement. It's named for Professor Fred W. McLafferty. He was born in 1923. It was in his lab where it was discovered. And so what was happening is when you had carbonyl containing compounds, you would get really weird fragmentation patterns. And nobody could really figure out why. It was just kind of this weird thing. And so what he proposed, right, because you get this enol radical cation here, is this mechanism where the electrons in the electron beam grab, for this double bond, grab that proton, right, after we've lost an electron here because we've got that positive charge. It grabs that proton and brings it back and forms that alcohol. This bond breaks, and it goes here to form a double bond. It's that double bond right there. These electrons jump here to form a double bond, and it's this double bond here. That's a breaking between the alpha and beta carbon there. And so it undergoes this rearrangement. It gives us an enol radical cation, and that's where we get a mass to charge ratio for this particular compound at right around 58. So when we look at this, this is particularly stable. So because that is particularly stable, that ends up being your base peak right there. Okay, so that's our McLafferty rearrangement base peak. It's not limited just to ketones, but it is characteristic of several compound classes like carbonyls, aldehydes, carboxylic acids, esters, and amides. So we do see that pretty often. It is asked about because it's a named reaction. And so if we were looking for a definition of a McLafferty rearrangement, it's just the molecular ion of a carbonyl containing compound that undergoes the cyclic movement of 6 electrons to produce an enol radical cation, right, and an alkene. Right, and so again, you can have lots of different rearrangements. I primarily worked when I did mass spectrometry with peptides. Lysine gave us a really interesting rearrangement. But these are some of the first rearrangements you'll see. They're very common. And again, there are much more out there, but they're really outside the scope of this course.